So welcome everybody to this last tutorial by the Quality Statistics and Reliability section of the Inform Society. So in this section, we promote interaction among scholars and practitioners in quality statistics and reliability with an emphasis on research and real-world applications. So currently we have more than 1,000 members in several countries and regions around the world. So this time we have the third tutorial from this QSR tutorial series. And I would like to take this moment to thank all the speakers, Dr. Juding, Dr. Peter Goose, and also Dr. Haitao Liao, who is going to give us the last tutorial. Thank you very much for their contributions to the section, to the society, and also to the field as a whole. So just in case you don't know, you can join the QSR section. And there are two ways. If you are already an Informs member, you can just add in the quality statistics and reliability section. We have different prices for students as well as for regular members. And if you do not want to have the full membership to Informs, you can also join just the QSR section alone. And to do that, you can go to the website. Here is a QR code that can direct you to the website of the section, or you can email Francis in order to request the form to pay the fee for only QSR. So we in QSR, we organize many events such as these ones. We have a nice community of people who like statistics, quality and reliability, and that we collaborate. So there is a very nice collaborative environment and learning environment in this section. So before we start, I also would like to thank the organizing committee for all the effort that they have paid into organizing this tutorial series. So a special thanks to Bill Fisher from JUMP, Hee-Young Kim from KAIST, and myself, Alan Vasquez. So we are the organizing committee, and then we thank all the participants and also the speakers. All right, so at this moment, I will stop sharing. And just one moment. All right. So for this last tutorial, we have Dr. Haitao Liao, who is the John and Mary Leap White Endowed Systems Integration Chair and a professor of the Department of Industrial Engineering at the University of Arkansas. Dr. Liao's research focuses on reliability modeling, fault diagnosis and prognostics, smart maintenance, service logistics, and other areas. He has authored more than 130 journal articles in top journals such as European Journal of Operational Research, Naval Research Logistics, and IISc Transactions. He is the recipient of multiple awards, including the NSF Career Award, the Alan O. Plate Award for Tutorial Excellence, and several base papers awards from multiple renowned societies. Dr. Liao is currently an associate editor-in-chief of the IEEE Transactions on Reliability and a fellow of the IASE. So, Dr. Liao, thank you very much for your tutorial, and now the floor is yours.
Well, thank you, Alan. So let me share my slide. Let's see. Can you see my slides?
Yes.
Okay, that's good. All right. Okay. Thank you, Alan, and for the invitation, and it's my pleasure to give this tutorial. I like to first give an overview of this tutorial. I don't want to read it, but this 2-hour tutorial is going to begin with an overview of the widely used reliability testing techniques, statistical models, and testing methods. And then I'm going to spend a little more time on focusing on several interesting technical challenges and also some practice solutions we came up with to solve those problems for that help engineer to when they actually try to develop highly reliable products. And the tutorial is the audience of this tutorial is I consider is pretty diverse. So focusing basically on some of the engineering students who have no a strong background in reliability engineering or statistics analysis can also learn something from this tutorial. And also for some researchers who have a very strong statistic knowledge and also domain knowledge in reliability engineering, you can learn something. Hopefully, you can learn something. And also for some industry practitioners, if you're interested in some of techniques or you want to learn some new development in academia, this would be a good source for you to learn, maybe just for your reference. First of all, okay, I would like to say some bad words about reliability people because if you look at this negative sides of reliability, we always talk about the failure, breakdown, loss, disruption, and fault, and degradation. That nobody likes these words. Okay, but when we talk to those designer developers, they don't like those words at all. But we to make them happy, we actually show them our positive side. We talk about reliability. So reliability is for some audience who has no your background or knowledge about reliability. I will just quickly read this. The reliability measures how consistently a system performs its intended function without failure over a specified period of time. And so nowadays we actually focus more on resilience, go from a reliability to resilience. Then we actually basically more concerned about how systems, well, the capability of the system to withstand and recover from disruption or failures. And the people think, okay, how big difference between, well, what is difference between the reliability and the resilience? How big the jump it is? If you're interested in this topic, I would like to share this paper published in 2024. Talks about the from reliability to resilience. And this paper is published in, it's a very short paper, but it talks about how we look at reliability, the linkage between reliability and resilience. And it would be fun to read. Now, and also as a reliability engineering person, I would like to acknowledge several pioneers in the reliability field. So, for instance, Weibull, he invented the Weibull distribution, which is widely used in reliability area. And the people, a lot of times, actually, industry people learn, attend some workshops to learn so-called Weibull analysis. And so they learn how to use the model and how to do data processing and how to explain the results from the computational result and to find out what should we do to the new product. And also Richard Barlow and also Frank Cross-Chen, they are pioneers in reliability, field of reliability. They provide a lots of new concept, well, at the time, innovative concept about reliability and maintenance. And also Bill Maker in Iowa State, he's a world famous statistician and focus more on statistical methods for reliability analysis. And also Dr. Win Nelson, he is also pioneer in accelerated testing. He used to work with Bill Maker used to work with Win Nelson. And also Dr. Allison from Rutgers University, distinguished professor there, and he's also a very famous professor in the areas of reliability. His most significant contributions is in accelerated testing and those testing plans, also production systems. And I cannot list all the pioneers in this one slide, but if you're interested in who actually contributed to the theory and the practice of reliability area, you can look at this article, even though it was published 22 years ago, but it's talked about the pioneers of reliability theory of the past 50 years. So even though it is old, in the past 20 years, more people actually contributed to reliability theory and practices. But it's a conference paper. You can take a look at it to get more information. And that's actually something I like to share with you. And also, let's talk about what reliability people do, just in case some of the audience has no background or knowledge about reliability. So, what do reliability people do? So, people actually, when they do reliability analysis or improvement, they focused on several layers. So, lots of people work on material and component level. They do focus on physics of failure, do accelerated life testing and degradation testing, and reliability growth tests and so on to find out, so to surface those potential failure modes and do something to eliminate those failure modes so that they can improve the reliability of the product. And then people combine to assemble those components together in order to produce a system. Then people also focus on system and product level reliability analysis and improvement. First, they do highly accelerated like testing, highly accelerated stress screening, and also system reliability optimization and so on. And then after the new product is developed, actually launched in the market, people buy it, people use it, then people get word about how this is the fleet, the reliability of the fleet of the product in the field. So then people talk about, develop some methods and models for predicting service demand, do service demand prediction, warranty planning, and also spare part inventory control strategy, and so on. So these are some of the topics a lot of people actually work on in the past 50, 60 years. And also, I want to share some of the very basic concepts. A lot of people, engineers, when they actually start learning reliability, they learn something called the failure modes and the effects analysis. And they focus on failure modes and the root cause analysis. For instance, they look at different type of failures, for instance, complete failure, partial failure, intermediate failure, or something like even in unintended functions. This is a very important type of failure modes because when we actually start talking about the AI system with AI capability, sometimes the system with AI capability can do something that is not intended to have. So this is a very important type of failure modes that our modern system may be based on this. And when people do this failure modes and the root cause analysis, they actually look at how to use so-called failure modes and effects analysis, FMEA, or failure modes, effects of criticality analysis, fault tree analysis, event tree analysis, and so on, to find out what can cause a system to fail and how to eliminate those failure causes. I would also like to recommend one book widely used in the industry. It's called Effective FMEA by Carl Carlson, published by John Wiley and Son. Even though it's old, but I think he has a newer version of this book. But I just want to share this book for some of the audience who likes to learn what FMEA is and how to use it in industry environments. Give you one quick example. For instance, people like to analyze the reliability of this system in here, this system, and they do FMEA to find the root cause, potential cause, failure modes, and also effects, and then come up with the risk priority numbers to identify which failure modes is extremely critical and how to eliminate such critical failure modes so that system reliability can improve. And also people use a fault tree analysis to identify the minimal cuts, and so that they can calculate the top event failure probability and the importance of some of the minimal cuts. Just want to share one. Actually, you just in a minute. I will show you one quick example, and also people like to do a lot of testing. So just beyond this, previously, just beyond this, just analysis. Analysis. Okay. Okay. And also what reliability people also do is that they do reliability estimation and improvement. So a lot of people actually with the engineer background and statistics background, they do experiment tests, actually do conduct experiments, especially reliability tests, to find out, to generate failure time data and also so-called degradation data to evaluate the reliability of a product or material. And some of the people actually in the material science and mechanical, they do they use a finite element, come up with a finite element model to do a stress analysis to identify the weakest link in the design, so that we can change the design, geometry of the design, change the material, change the surface profile, and then they can improve the reliability of the product. And also a lot of people actually call the testing engineers. They conduct experiment, reliability tests in the laboratory to expose the material and product to some stressors called stressors, environment conditions, extreme environment conditions, and for instance, temperature, humidity, and the current, and so on, to surface those failure modes and do and estimate reliability based on failure time data or degradation data, and also just basically to come up with some reliability estimation. And then they assemble those component level reliability estimates together in order to estimate system reliability. And also, a lot of the research have been done on so-called reliability redundancy allocation problem. And for instance, well, the goal is to use a cheaper material and or less reliable components to make a highly reliable system. So a lot of researchers in this area, for instance, Dr. David Coit at Rutgers University, has done a lot of work on reliability redundancy allocation problems, especially one of the most widely cited papers is how to use some genetic algorithms to deal with reliability redundancy allocation problem. And if you're interested in such topic, you can actually go to his website. And give you one simple example. So it just actually came a couple of days ago. So a group of people at the University of Arkansas, they actually developed, they win an award. So the first place at the International Aerospace Power Electronics Design Challenge. What they did was just simply remove one single point failure in their power electronic design. So they consider that if this device is used in power electronics, it's used in outer space, no one can fix it. So if one failure happens, entire system going to fail. So they find out, identify the several single point failures, then they remove the single point failures, and so that the system reliability. So they only use very simple concept in a reliability engineering to actually make their product very reliable, even for outer space application. Now, and also I also notice some of the audience have very strong data analytics backgrounds, so they are interested in maybe what data analytics can do in product design and operation. Let's talk a little bit about that. We use data analytics to do reliable estimation and verification. Yeah, I'm going to spend a little time just in a minute talking about how we conduct reliability testing, how we collect data, how we do the test, how we do the data analysis. And also we can, decide that how to optimize the test plan so that we can collect data in a more efficient way. And also people use, data analytics to do quality control. So during for manufacturing time and manufacturing stage, so that we can actually make the product as we want it. Actually, for instance, we have a CAD model. We want to make our product as close as possible as the CAD model shows. And also we do prognostic and health management. A lot of people do that. So basically they have collect the sensor data and put sensors on some individual system and keep monitoring health index or signals. So they use the health index to quantify the system health and also predict the remaining useful life of the operating system. Just before the failure occurs, they can actually provide some useful information so that we can do maintenance as early as possible and also at the right time and the right place. And also, while people use data analytics to do a fault diagnostics, this is especially very useful for a larger system, not just simple like a car. But doing fault diagnosis in a car is easy, but what if you're dealing with a large system like a nuclear power plants and a ship system and so on? Then a fault diagnosis is going to be very important. One of the important things is when we use sensor to measure health index to actually monitor a system health, many times the sensor may fail before system fails. So this is a very ironic problem, but how to deal with this issue has been studied. Well, actually, this method has been published, I think, in many journals. And people start talking about how to identify sensor failures or system failures, how to use sensor redundancy or data, the signal redundancy in order to identify if the sensor failures or it's a system failure. Now, let me spend a little time talking about the testing. I hope it's not too fast. I speak fast, but I hope this contain audience. Let's talk about testing. So just in case some of the audience has never uh, seen testing equipment, I want to share this. This is a reliability testing equipment in my lab at the University of Arkansas, Industrial Engineering Department. So on the left, you see this is environmental chamber. So in this environmental chamber, it can change. We can actually change its temperature, humidity, and also we can apply shocks and random vibration or sinusoid vibration. And also, of course, well, we have to consider when we do testing, we have to consider its chamber capability. For instance, this chamber can do temperature ranges from negative 45 degrees Celsius to 190 degrees Celsius, and relative humidity can go from 10% to 95%. So when we actually conduct reliability testing, we have to really consider the capability of the test equipment we have. On the right-hand side, this is called ED shaker, which create actually the vibration, and you have a monitor there. You can change the setting of the vibration. For instance, you can do a random vibration. You can do a cyclic vibration for the sinusoid or some pattern or the vibration. It just depends on the shaker's capability. Just in case for some the audience who has never seen reliability testing. Now, let's talk about what type of reliability test we may have. So first one is the operational life test. So test, basically we just test units. Those test units are posed to stresses and environmental conditions at a typical operating condition. Basically, it's called use conditions. So for instance, if you use electronics device in a room at room temperature, you tested your device in room temperature and collect the lifetime data. This is called the operational life test. But of course, to see if as our product has become more and more reliable, getting failure time data under the typical operating conditions is going to be extremely difficult, and it takes a lot of time, long time to even actually see a failure. Without failure time data, we cannot. Of course, it's going to be harder to construct, failure time distribution, the failure time distribution, in order to estimate the reliability. So it's hard. So then people come up with, okay, what about this? If I expose the test units to higher, for instance, severe than normal condition. For instance, higher temperature, higher relative humidity, a higher temperature, a higher current, so that those devices can fail in a much shorter time. So this is the concept of accelerated life testing. So ALT. Basically, it's a process for predicting the reliability of a new product in a shorter period of time by time or stress acceleration. Okay, I will talk about this in a minute. Well, of course, people think, okay, well, if I will be more aggressive, even though I cannot collect the failure times under normal operating condition, but if the product degrade, for instance, the strands of a material are going to degrade, and the crack is going to initiate and keep growing in a mechanical part, as long as I can monitor such so-called degradation data, we do not have to wait the product to fail. So I still can collect the so-called degradation data and build a degradation model to predict the reliability of the product or the device. So this is the concept of degradation test. Of course, we can be more aggressive if we apply, the more severe condition, expose the part test units to more severe conditions, so degradation can occur in much faster. So we can observe degradation data in much shorter time. Of course, what the challenge is going to be, I got, accelerated degradation testing data, but I also know the conditions I tested the test units, but how to do extrapolation based on so-called accelerated degradation tested data, how to predict or extrapolate reliability of the product under the normal condition. I'm going to spend a little time today talking about these basic concepts. All right. So needs for accelerated testing. So especially nowadays, technology advances. in material science and design and manufacturing. So we can make the product or material extremely reliable. And we're trying to build a highly reliable product, but we only have a limited time for research and development and for testing. And to predict the reliability of product under different operating conditions is another very important subject. If you're testing, testing your new product, and you estimate reliability of the product under a specific use condition, but if you change the use condition, you should estimate the reliability of your product in the well by considering different operating conditions. How to do that? It needs to build a model that is called accelerated testing model, and to do this. And of course, another one application is the prognostics under time varying operating conditions. So if you already finished the design and you launch the product to the market and people are going to use it, so but the time operating condition may change over time, not fixed. So well, maybe the weather going to change, relative humidity is going to change, the current is going to change. If those conditions are changing over time, how to predict the remaining useful life of your device is very challenging problem. So, all right, so neat. So if you're interested in what accelerated testing can do and the future of accelerated testing, I'd like to just share this article with you. Again, it was published. It's a short paper published IEEE Transaction Reliability 2 years ago. Let's talk about accelerated life testing, history and the future. And especially let's talk about, and also, of course, cover something about maintenance. Well, I think the maintenance and accelerated testing has a very natural connections. And again, you're welcome to read this article when you have time. Now, let's talk a little about accelerated life testing concept. Assuming, as I said, if you have a goal to estimate the reliability of a product, your newly developed product under normal conditions, but the failure time data is difficult to collect. So I don't want to wait until I get some failure times. Well, of course, all the units are censored, and I cannot fit failure time distribution to the data, all the sensor data. So what I can do is I expose some of test units to higher, well, actually severe condition. Let's say in this case, Z1, Z2, Z3 are more severe than Z0, which is a normal operating condition. So because of the conditions are more severe in the test environment, so I can collect some failure time with a sensor, of course. Then I build accelerated life testing model. I can do extrapolate. To extrapolate the probability density function of the product, the failure time distribution of the product under Z0. So this is a basic concept of accelerated life testing. And of course, while the reliability function can be expressed as probability that the lifetime is greater than T, and of course to infinity, when you consider different stress conditions. All right. So, but when we do accelerated testing, some of the problem needs to be addressed. The first one is what failure modes are we or are interested, and what type of stresses should be applied, and what is the number of stress levels, and how are the stresses applied, and what is the number of units to be tested at each stress. So you talk about this. So this actually are some very practical problems a test engineer should actually are faced with every day when they do reliability tests. Now, regarding type of stressors, so widely used in reliability testing, we mainly consider temperature, high and low, and temperature cycling, and the power cycling, especially for those power modules. People in the power electronics industry, they like to do active power cycling to see if every time you do power cycling, it causes a shock to the power module. They want to see if how reliable the power module is under subject to power cycling. Of course, vibration shocks, voltage condition, electrical current density, and this is very important for currently new in microelectronic industry. They're interested in developing silicon carbide, the new semiconductor material, which can handle high temperature and also high current density. But this new material is so new, not well, several years ago they started doing it, but not many people have experience in how to analyze and how to find the failure modes of such devices, and how this such a device product performs at a high current density. So another one is a charge discharge current, and this goes very important for the for some people who is working on lithium ion battery, and they actually they consider the charge discharge current and also that's the charge and so on. So those are some factor well stressors people would usually consider when we do sort of reliability test. Of course, electrostatic discharge is also widely considered in microelectronics industry, and the radiation, for instance, like alpha particles, and people working in aerospace and outer space and NASA, they consider testing their devices or certify their devices by considering, how reliable those devices are under radiation stressor. Well, if you talk about the stress loadings, we can consider constant stress, step stress. And I'm going to show you this. So the first one is constant stress, step stress, and cyclic stress, and ramp stress, and ramp step stress. So different stress loadings can be considered in reliability testing. Well, then talk about data collection. If you have a sample of n components allocated and tested at different stress levels, the widely used data collection methods are the following. So you can consider collecting exact times plus minus censoring. Well, consider censoring or without censoring. We might be dealing with the so-called complete data, failure time. If there's a run to failure, of course, if we consider all the components fails before, well, when you stop the test, then it's probably going to take a longer time. And then people consider type 1 censoring, so stop test at a given time t, or type 2 censoring, stop test at a given number if you already received see a certain number of failures. Or sometimes you'll consider random censoring. And in addition to collecting exact failure times, those people also collect group data. And you only know during this period of time I have 3 failures, but I do not know exact failure time of this 3 failures. But people just use such data to estimate reliability. And also people consider the truncated data in different ways. All right, so now people have the data. How to estimate reliability using accelerated life testing data, testing model. Well, there are several widely used accelerated life testing models. The most widely used is called accelerated failure time model, in short AFT model. So what it does is to scale the time by under different considering the scaling effects of the different stress levels. So for instance, if you change the stress level, this R function is going to change. Well, it's a function of the stress level. And the theta is a parameter for this so-called life stress relationship. Of course, pharmacy's cumulative distribution function, you can find a corresponding Heather function, and of course, reliability function, and so on. And of course, mean residual lifetime. And another widely used ALT model is proportional hazards model, and also some extension of such model. The basic one is when they consider the proportional hazards model, they do actually consider proportionality of hazards. So, unlike AFT model, which scale the failure time, proportional hazards model scale the hazard function. So it's just on the right hand side, you see the proportionality. You see the log negative log R, which is these are 3 lines actually are parallel to each other, and this shows proportionality. And of course, this actually is the cotton. Well, people a lot of times they do not specify the baseline failure, baseline hazard rate. That's why this method is called a semi-parametric model. AFD model is actually a parametric model. You have to assume underlying failure time distributions. So there are several widely used AFD model, and specifically those probability distributions have been widely used in the FD model. For instance, exponential model, exponential distribution, Weibull distribution, other distribution like a log-norm distribution, inverse Gaussian distribution, a gamma distribution, and so on. And those probability distributions have been widely used in reliability engineering. Now, I'll give you a quick example into how people develop accelerated life testing model, how to use the model to estimate reliability or extrapolate the reliability or predict the reliability of the product under different conditions. So in this example, this actually the data is collected 15 years ago, a long time ago. This is about the miniature lamps. We actually did accelerated life testing on those miniature lamps in the laboratory. And we consider three different conditions, three testing conditions: 5 volts, 3.5 volts, and 2 volts. And also we considered well, actually just like this, so three conditions, and put it in there. Just consider the collective failure times. Of course, we do not wait. We did not wait all the components to fail. We consider censoring. So here, this table shows the accelerated life testing data we collected, and also, of course, to do analysis, we actually just standardize the voltage stressors, so that we can focus on the range of the stress from negative from 1 to 0, and so on. And we use log-norm distribution, where we consider the one of the parameters that actually the mu as a function of voltage. So this is the model, and we just fit the model using our accelerated life testing data, of course, using maximum likelihood estimation, and we can get find the parameters of this model, and then we plot the reliability function, PDF, and failure rate, and also we use Cox-Snell residual plot to show how good the fit is. What you see here, this is based on the Cox-Snell residual plot. It's good, but not great. So you may think, okay, the model may not be the best model, and we probably can do something to improve it. Well, so now we thought about it. Okay, well, we would like to highlight some of the existing and new challenges. So first of all, when you talk with reliability engineers, a lot of reliability engineers in the field, a lot of them do not have a strong statistical background, and also as time in the modern days, so we are developing some new device, using new materials. There's so many unknowns due to fast technology advances in material science, design, and manufacturing. So some new new materials are new to us. So in order to find a failure time distribution that provide actually really represents the underlying failure time distribution well, it's not easy because we do not have a domain knowledge, not at all. So everything can be new to us, and also we do not know exactly lifetime stress relationship in our book, in our mind. So because everything's new, so we do not know this. And also for those, like I said, some practitioners, they have limited training in statistical analysis. So it's going to be hard, always hard, for them to determine which probability distributions they're going to use, what life of stress relationship they need to consider, so that they can process accelerated life testing data. It's hard. So, and also another challenging problem is, so a lot of times when people in industry, when they report failure times, they do not provide the actual failure times. They provide some so-called aggregate failure time data. So, for instance, okay, from time 0 to after 10 hours, then it's okay. I have 5 failures, but the last unit is still working. So, if you use this type of data that they provide, but if you use the regular failure time distribution to analyze such data, you probably have to be facing with intractability problems, so that you cannot find This is considered convolution of several random variables, and the distribution is not tractable. So now people can ask. So when I gave a tutorial to industry people, people said, "Okay, tell me about this. Help me with this." So I do not have a strong background in statistics analysis, and of course, well, there's some commercial software over there which can help us determine which distribution should be used, but sometimes these distributions do not provide good fits. So can you come up with a generic ALT model so that I can simply enter the data into your package and you click several buttons and your model should be strong enough, actually it's capable enough or robust enough to handle different type of failure time distributions and can also mimic the not all kinds, a wide range of life stress relationship without a person to specify those relationships or failure time distribution. So in other words, can you come up with a generic ALT model so that I can simply enter data and the model gonna tell me what the reliability is? Well, when I do reliability prediction. So then we thought about it. Okay, well, things we want to come up with one generic method, we need to consider a generic or more powerful distribution that can mimic the lifetime distribution of non-negative random variables. So people probably know, okay, phase type distribution is one of those. So if you I want to just down this chart only shows one widely used phase type distribution, Coxian distribution. This is the continuous time Markov chain associated with the Coxian distribution. Absorbing time, absorption time from the initial stage to the absorbing state is actually follows Coxian distribution. And of course, there are other type of phase type distribution out there. For instance, like hyper Erlen and hypo Erlen distribution out there. They're also very powerful, but I personally like Coxian distribution because it has a very strong capability to mimic any probability distribution of a non-negative random variables arbitrarily close. That is just something I really like. So in 2017, a long time ago, I thought about how to develop a phase type distribution based AFT model. As I said, well, it's an AFT model. It's simply you express your consider life to stress relationship as that scale, the time. So in this case, if we consider AFT model based on the phase type distribution, and here it shows the cumulative distribution function, probability density function, and a header function, and also to show the sub-generator generator matrix, and so on. But I thought about this. AFT model is so limited. It actually captures the scaling effect of stress on the time, which can be probably improved significantly. So then we consider a different thing, which is make an improvement. So we consider a Coxian-based method, a model, for modeling ALT model, where we express those transition rate, go back here, those transition rate, lambda 1, lambda 2, lambda 3, and so on. It's a function of those stress level of different conditions. So we can actually make the model even more powerful. So basically, it's not the stress. We're not just simply do scale the time, and also gonna change the transition rate in this continuous time Markov chain. So it have more capability to actually model life of stress relationship, which cannot be done by the AFT model. All right. So, and of course, when we develop such model, we also need to consider one constraint. So structural constraints for different stress levels, which means if you change the stress level, the continuous time Markov chain will not change. If you have, for instance, a 3-stage or 4-stage continuous Markov chain in your model, if you change the stress levels, this Markov chain structure will not change. Well, it's still going to have 4 stages. So we superimpose such constraints when we develop this model. and develop this coxine-based model. And also, of course, we need to use when estimate parameters, things we do not, we don't, when we do testing, we only observe absorption time. So all the soldering time in the intermediate stages are not available. So that's why we need to use so-called actually constructed like the function, but we need to, we actually will construct it, develop the expectation maximization method algorithms to do the estimate of parameters in this model. And when we also want to come up with the interval estimation for reliable estimates, we can use either parametric methods and also this non-parametric bootstrap methods as showed on this chart to come up with a interval estimates for reliability function or failure time quantile. I'll give you one example. The same problem, okay, same data set, as I showed you. So in here, we also want to compare the capability of our newly developed costing-based ALT model to see how powerful it is. We compare our model with the so-called mixture Weibull. Of course, if people know mixture of mixture distributions actually provide another way to mimic, complex probability distributions. In this case, we consider mixture Weibull, and we estimate the parameters in the mixture Weibull using the data we collected in here, and we do prediction. Now we compare this. Okay, we compare the first two. It shows mixture of a three Weibull distribution, and on the right, top right is actually mixture of four Weibulls. At the bottom, we show the three-phase coxine and the seven-phase coxine. As you can see here, actually, the three-phase coxine distribute ALT model already provide very good fit to the data. And as a matter of fact, the new method outperforms widely used mixture Weibull distribution with respect to both statistic performance and also model complexity. We actually compared number of parameters at three-phase coxine actually provide the best in terms of number of parameters, also the statistical performance. Well, and of course, we'll also want to use this actually shows the parametric methods to come up with confidence interval for the estimates based on this data set. Now, some works on pH-based ALT models are listed here. The most recent one, the oldest one, is actually published in 2017 in a book chapter, and also we come up with some actually publication in conferences, also a journal. And the most recent one is actually the last year published in the RAMS conference, where we used coxine-based methods to analyze censor the aggregate failure time data using the coxine distribution. And if you're interested in such a method and publication, feel free to read those articles. Now, and also I want to talk about, then switch gear, we'll talk about degradation analysis, just for some audience who has never done this before. And why we do degradation analysis? Because it has a clear physical meaning. We measure degradation characteristics instead of failure times. And for instance, like a strength, like a cracked lens, and loss of the light intensity, and so on. And also sometimes we measure the vibration, by doing vibration analysis in order to capture the, for instance, the vibration power of vibration and so on, and on this on certain characteristic frequency. And also we look at how we can use degradation analysis to significantly reduce testing time. As I said, instead of monitoring failure times, we collect the degradation data, and we can do reliable analysis before failure to occur, which is actually big time saving method. We basically can evaluate reliability of the product without waiting for actual failures, and we can also be more aggressive. We can test, units from material under accelerated testing condition, so-called accelerated testing, a degradation test, so that we can reduce testing time further. Now, I'd like to share some of the techniques. One technique is actually widely used by practitioners in the field. So as I said, not many practitioners, engineers have training, enough training or mathematical background in to do degradation analysis. But what they have learned is uh, they can actually collect the failure time data and fit probability distribution to the data. So they can do so-called wipe analysis and do reliability estimation. This they have already learned. So, but when they are dealing with degradation data, they have no clue how to deal with this. But people come up with very simple but very intuitive methods so that they can use what they have already learned. This is called the pseudo failure time method. Now, if you look at this chart, I have those degradation data, and DF the failure time, failure threshold. So when the degradation process crosses the failure threshold, we consider this unit is failed. So what they do is they do regression, fit curves to the data they collected. Well, of course, this should be non-destructive testing, so that you can collect the degradation data, multiple degradation data on one single unit. So they collect degradation data over time, then the fit curve, then find when this curve crosses a failure threshold. Because, of course, intuitively, this becomes a failure time, but this is not actual failure time they collected. That's why it's called a pseudo failure time. So when they collect this pseudo failure time, just find those pseudo failure times, they use those pseudo failure times, they fit probability distribution to the pseudo failure times, then they can estimate reliability of the product. Of course, what they're using is degradation data instead of actual failure times. So this is what practitioners often do in the field. But as I said, they do not have a strong background or training in to do degradation analysis, like researchers or statisticians. Well, of course, in 1993, Dr. Meeker and S. Kolba, they developed the so-called general path model, very innovative methods to analyze the failure time, degradation data. And they published this paper in Technometrics. At first, one is 1993, and then the following version is they talk about accelerated degradation tests using a general path model, and also other type of models available. And Wiener process model widely used, which can be used to monitor model monotonic degradation process. And the gamma process can be used to model monotone increasing degradation process. And recently, not recent actually, even though this paper was published 2014 by Dr. Ye and Chen in Singapore, they considered using inverse Gaussian process as a one degradation model, which is currently has been widely used and well cited in the field. And now let's talk about something even more challenging. Well, sometimes we have to, when I talk to some reliability engineers in the field, they actually dealing with something like this, especially mechanical engineers. When they look at the degradation process, they have to deal with the so-called degradation initiation. In other words, so degradation process starts after a certain period of time. Yeah, for instance, in this case, while they collect the failure degradation data, but actual degradation start not from time zero, after a certain time period, degradation starts. Well, this happens when one example is crack initiation. If you look at the mechanical components, either the shaft or something, or case or housing, crack starts after a certain period of time, but this crack initiation time is not visible. It's not collectible. Actually, you cannot do that. So when people start monitoring, start collecting degradation measurements, the degradation process has already started. So that means degradation initiation time is missing. I cannot do it. So then what practitioners do was use the pseudo failure time methods, but they fit the curve to the degradation data they collected, and then do extrapolation downwards to find pseudo initiation time, like that. The initiation time, of course, which is estimated, but this is the intuitive method they come up with. And they do this for all the degradation process. Well, they collect the degradation data, they collected. Of course, they also, find the pseudophila times, by, extrapolating the curve, onto the curve of process, the failure threshold. Yeah. So then come up with these methods they can still estimate the reliability, even though they probably do not have a solid training in degradation modeling. But this is what they do. Now, of course, well, for statisticians, for researchers, we can use those methods to come up with some, better way to deal with the process. But I want to share one interesting problem we were faced with. It's even more challenging. In here, we have to deal with degradation initiation, but of course, we cannot we cannot collect or find the degradation initiation time, and whenever the product start degrade, so started degrading already. And also, when we collect data, we can only collect one data point from the test unit. This actually is motivated by one project we've done with the industry. It's we talk about the solder joints reliability. We tested the solder joints under solid conditions, but when we collect the strength, what is called the shear strengths, we put this test unit after maybe like 100 hours. We tested, but we can only after we measure the shear strength, we destroyed the solder joints. So in other words, we can only collect one degradation measure from each test unit, and also we do not have information when the degradation starts. So basically, we have a missing value for degradation initiation time. Then we develop the methods, consider the distribution of the initial fill time distribution, and we come up with use a gamma process to actually model degradation process. But things we do not have degradation initiation time, we have to rely on EM expectation maximization algorithm to estimate complex parameters. And in this process, this research will also consider random effects model and fixed effect model. And based on the data we collected, it turns out this two models is not significantly different. So we can just stick to the fixed effect model. So let me stop here.
So I think we have reached the 2 p.m. Mexican time mark. So we should have like a 5-minute break. So before we go into the break, are there any questions from the audience? So one question, Haitao, is I think you have talked about products mostly in the engineering field. Have you worked with products like food products? So do they have the same challenges in food, like degradation of?
Good question. So recently, my students are working on so-called cold chain logistic problems. They consider food. One of the product we consider the green belt. So you can consider actually the two stages. So first you have to store food in a storage center, in actual storage. So you have the temperature setting, and also then when the times comes, you just start delivering the food to customers. Then they put it on the refrigerated truck, and you have to set the temperature, and if you select the routes so that you can hopefully you do not damage too many products to satisfy the demands. So this is we actually came up with this so-called the two-stage stochastic optimization problem. We solve it, and it's currently under review. So they consider both the temperature setting going to affect the degradation of the food, and also the transportation time, basically the time how long you go from the storage to the customer site, It's a random. Is it a travel time? Is it a transit time? Is random. You have to consider traffic condition and so. So there are many things to be considered in such modeling process.
All right. Thanks. So if there are no questions, then let's start the break. So just 5 minutes.
Let me keep sharing.
Yeah, we have 1 more minute left.
Okay.
All right. So welcome back, everybody. So yeah, let's resume Haitao. Thanks.
All right. Okay. Thank you. I will be quickly go through some of the slides. And also, I'd like to share some of the ideas about, so actually, the people probably already know that use of accelerated degradation testing can save a lot of testing time and effort. So, for instance, you want to actually estimate reliability of the product in a normal condition, but this takes time to collect the degradation data under normal conditions. But it can expose the product in under the severe than normal conditions, so that the product can or material can degrade much faster. So we collect data, and then reliability estimate can be extrapolated. I want to give you one example. So this is the data actually showed. I think some. I think I collected them many years ago. So we basically conduct a 250-hour test to predict the reliability of LEDs at 20,000 hours under 40 degrees Celsius and 10 milliamp. This is a big time and the cost of saving technique. So if some of them you're interested in looking at the data, you can feel free to read those papers and use the data. And this is some works on degradation analysis, especially the one of the recently published in IEEE reliability. Reliability is a generalized functional mixed models for accelerated degradation based reliability analysis. Feel free to look at those, where we have a multiple degradation measures, multivariate degradation data. And also now let me switch gear to talk about something more theoretical. So it's about the equivalent accelerated testing plans. So give you a very quick overview. So when we planning accelerated testing, we need to consider several different variables. For instance, stress levels, Z1, Z2, Z3, and then also we allocate some test units to those test units. And then we talk about sensor time, so when to stop testing after the sensor time comes, some units, even though they're still working, we remove it from the test. So we have some failure time data and also sensor time. Then when we actually try to plan accelerated testing, we need to consider some objective functions. Most widely used objective function like minimizing asymptotic variance mean time to failure, minimizing asymptotic failure asymptotic variance of the failure time quantile and reliability, or asymptotic reliable variance of a CDF, or consider some criterion like D optimality, A optimality, C optimality. So now, just very preliminary information. So we consider uncertain propagation. So we consider how to find the asymptotic variance of some function of your unknown parameters, estimate parameters. And if you consider this, is called the delta methods, and you see it from Nelson's book. We have if you're interested in estimating asymptotic variance of G, for instance, reliability, or reliability function, or CDF, or mean time to failure, failure time quantile, and basically can be expressed as follows. One is the gradient function, which is which is a function of a G with respect to derivative, partial derivative gradient. This is a G function with respect to the unknown parameters, and this is the variance covariance matrix in the middle. You can get it from Fisher information matrix, and then we can simply consider, okay, this on the left, this part is the A vector, and on the right is a prime vector, and on the right is become actually the column vector, and on the left is the row vector. So what we do is we want to determine how to determine those decision variables in order to, for instance, minimize asymptotic variance of the G, something like that. For instance, minimizing the asymptotic variance of reliability function, like that. So, and formulation of a traditional accelerated testing model like this, we want to determine those decision variables, value of those decision variables, in order to minimize our asymptotic variance of something, G function, by considering those inequality and equality constraints. But now, some practical issues come up. So first of all, in accelerated testing plan may have some good statistical properties, but it's technically infeasible. Remember, we are trying to do the test using our testing equipment, but the testing equipment has some capability. Well, cannot, for instance, this chamber can heat up from 90 degrees Fahrenheit to negative 90 degrees Fahrenheit to 75 degree Fahrenheit in 20 minutes. So it's not cannot say I cannot jump from negative degrees Fahrenheit to 75 uh, degree Fahrenheit in 1 minute. Cannot do that. So and also the cool down from the high temperature to low temperature also takes time. So you have to consider when you come up with such stress loadings and can my testing equipment do it? This is one practical problem. And also sometimes we are interested in some of the statistical properties of the AT model, AT plan needs to be improved. For instance, this is the variance covariance matrix estimate. And this term, variance of the theta 2 parameter, which is the variance of estimated coefficient of load. So if you're interested in minimizing or try to reduce this variance term, you have to change your accelerator testing plan. So for instance, if you want to do prognostic, um, this theta 2 is associated with a load. When the load changes, you better, well, in the model, it's play a very significant role in the remaining useful prediction. You have to make sure that I try to minimize the uncertainty in this parameter estimate. So now, to deal with this problem, we actually had the NASA project. We want to actually investigate what is called the equivalency of accelerated testing. So here's the definition we come up with. Of course, more people may come up with different definitions. Two AT plans are equivalent if they generate the same objective function. For instance, if they generate both testing plan generate the same asymptotic variance for reliability estimate for the normal use conditions or asymptotic variance value for mean time to failure. And this is the definition we come up with, but as I said, people may come up with different definitions. And we dig into this problem. We developed so-called, well, this actually shows the structure. Well, we come up with so-called general equivalent AT plans, and we also consider type 1 equivalent plan with a special case of general, and type 2 equivalent testing plan, and type 3 equivalent testing plan. I'm going to go through these very quickly. So this is notation, let's forget about it. Now, let's talk about the theory of equivalent AT plan. Easiest one is general equivalent plan. So basically, if I have two testing plans, and this is the variance covariance matrix associated with these two plans. Remember, each term in this variance covariance matrix depends on how you set the test, how you set it up, right? Basically, depends on the decision value of the decision variable. So first, let's make sure, okay, the general equivalent testing plan, and just use the definition. So basically, the two asymptotic variance of G are equal, are the same. Objective function the same. So now I just want to determine, okay, if I already know the design for X, like the benchmark design, I want to come up with alternative plan that generate variance covariance matrix Y that give me the same objective function, so that these two testing plans is going to be equivalent. So now another one is a more extreme case. Of course, I set this, for instance, well, there's two objective functions are the same. So if the X matrix and Y matrix are exactly the same, it's the most extreme case. Then if X matrix and Y matrix are exactly the same, of course, well, this two objective functions should be the same. Well, of course, we need to solve these number of nonlinear equations, well, which depends on the size of the variance covariance matrix. If this is the n, well, the n is the size of the matrix. So you need to solve these number of one half n times n plus one number of nonlinear equations in order to determine the equivalent testing plan for this type. I'll call this type 3 equivalent plan. Now, here's the theorem we developed. Well, actually, basically, people, researchers are going to say, okay, wow, I want to make this two matrix exact the same. So can we do that? So this theorem says, talking about existence of type 3 equivalent plan. I don't want to spend too much time there, but it just shows the theorem shows if you can show that in such case, such conditions are satisfied, you can find type 3 equivalent testing plan. Basically, you can make two variance covariance matrix exactly the same. And for practitioners, they do not care too much about existence of a testing plan. They just give me a method I can use to find type 3 equivalent testing plan. So this is the modified one parameter in operator embedding algorithm we developed. So you follow these steps. You can, as long as the type 3 equivalent plan exists, you can use this method to find the type 3 equivalent plan. Now, give you one example. If you consider a simple log linear exponential model, where the failure rate under stress z can be expressed as lambda z equals exponential theta 0 plus theta 1 z. So that Sawtooth's cumulative distribution function can be expressed as follows. And then suppose the baseline estimates of parameters are the following: theta 0 hat, theta 1 hat. And of our interest is to find the estimated reliability function of the product under the standardized use condition, well, consider what the z0 equals 0 at time 1,000 hours. And we want to estimate corresponding reliability at this use condition under after 1,000 hours. And the gradient vector A can be expressed as follows. Then use our methods. So assuming you already have a testing plan in your mind, it's satisfied your requirements, statistical requirements, precise enough, then we can calculate symptomatic variance for this testing plan. And our objective is to find a 3-level constant stress ALT plan that give the same value of asymptotic variance as the benchmark testing plan. So for the desired plan, the number of test units is, we have considered 70 units, and Z3 equals 1, and we'll consider type 1 censoring. And we use our methods, and this actually just derived this equations. And the goal is to make the two variance covariance matrix to be the same. So use our method. While this actually shows a tedious, through a tedious proof, we show that the solution exists based on the theorem number 1. That exists, then we use one parameter embedding method to solve it. And we find that, okay, to solve the associated of the system of nonlinear equations, and with these initial guess, and find out the final solution are the following. Here, down here, the second line in red. So we can show that the variance covariance matrix are exactly the same. So that objective function will be the same. In other words, we use another alternative testing plan that can generate the same estimation precision as people expected. Now, another one, a type 2 equivalent plan. So we relax some constraints. We relax it. So what we want to do is for type 2 equivalent plan is we make sure this column, okay, in here, this is highlighted on the left, the column or row, they're the same, actually symmetric. So the column on the left, exactly the same as column on the right. And also actually length are the exactly the same. Not lengths are the exactly same, but not the two columns may not be the same. But what we want is actually A times this vector, which is the linear combination of this vector, and the equals linear combination of this vector on the right. If they're the same, then of course the objective function is going to be exactly the same. And we can also show that this is another theorem, the prohibition rule for type 2 and type 3 equivalent plan for 2-parameter AT model. And it says basically that for 2-parameter AT model will be type 2 equivalent plan for a given AT plan if it consists of only type 3. In other words, you want to come up with type 2 equivalent plan, and turns out your resulting test plan must be type 3 equivalent plan. You make the two variance matrix exactly the same. And there's some conditions you want to spend too much time on it. And also another propositions of prohibition law for rule for type 2 and type 3 equivalent plan. When the gradient matrix looks like this, it's 0 and plus some terms which may not be 0, then the two plans are actually type 2 equivalent plan becomes type 3 equivalent plan. For instance, if your the normal operating condition is 0, so put a 0 here, this term of theta 1 times 0 does not exist. So then your the gradient, your vector, one of the terms should be 0. Okay, one term should be 0. So in this case, the type 2 generative plan, equivalent plan becomes type 3 generative plan, equivalent plan. Now, one example, so equivalent to type 2 equivalent plan, we consider this, and the equivalent to plans give us these settings for those decision variables. So basically, the type 2 equivalent plan it's generally the same objective function, but the decision variables may be different from the general plan. And as a matter of fact, the resulting covariance matrix looks like this. So you see here, the Y matrix is based on this plan, and this X is the original variance covariance matrix, and they are exact the same. And actually, its result is obvious because it actually becomes a type 3 equivalent plan, and because of proposition number 1. And so, in other words, even though we want to develop type 2 equivalent plan, but it turns out we get type 3 equivalent plan. And that next one is type 1 equivalent. We can just keep relaxing constraints. So what we do is make sure, okay, well, there's two objective functions the same, as long as make sure all the column vector, this column vector on the left and on the right are exactly the same. Well, actually, A times is the weighted or linear combination of this column vector, of the linear combination of this vector, and they're exactly the same to satisfy this equation. If they're the same, then the overall objective function should be the same. So in this case, we can actually do more. If somebody also wants to, okay, let me do this. Let me first generate a type 1 equivalent plan, and also I want to consider additional criterion. For instance, if I consider de-optimality, so basically just try to minimize the determinant of a variance covariance matrix resulting variance and covariance matrix, we do that and also consider the definition of a type 1 equivalent plan. We do that, or just for some animation here, doesn't matter, just try to shrink the volume of this space. And we do that, so, too many, okay. And we do that, so if you consider de-optimal, of course, people can also consider a-optimality, or you consider to minimize a specific variance of specific parameter estimate. You can do that. So if you consider this example, so de-optimal type 1 equivalent plan, and it turns out they got these variable the settings for the Z1, Z2, and the unit allocation to those stress levels, and also the sensory time. And now I see here the resulting covariance matrix. Y is not same as the benchmark, the variance covariance matrix in our benchmark plan. They're different. And as a matter of fact, you can see here, this term is reduced. So variance of theta 1 hat is reduced, while overall the asymptotic variance reliability estimate is not changed. So this shows you can actually play with such equivalent testing plans to satisfy some of your specific needs. All right. So, and also we have I can also provide some geometric interpretation for that. The type 3 plan is you just simply make sure that the vector in the variance covariance matrix in a benchmark testing plan or the equivalent testing plan are exactly the same. Type 2 is actually these vectors x and y. They're actually on the same cone. This same cone, yj and xj are on the same cone, and yj plus 1 and xj plus 1 are on the same cone. And this the A is the gradient vector. And type 1 is these two cones share the same bottom, but y minus x should be orthogonal to the gradient matrix, the gradient vector. In general equivalent plan, you have a more freedom to find, the column to decide determine the column vector for the alternative plan. Now, it's a very interesting problem, and people say, okay, well, you developed some theory about it, how we use it. I want to show you one interesting problem after we develop this method. I'm going to show you this is the this method actually going to generate actually is generating profound impact on how new products are developed and tested. Now, let me show you one thing. Okay, well, when I start doing testing, when I was a student, I collected the data. Well, actually, I do this test. I put the power meter on the power line and measure the power consumption of this chamber. So when I did this, I consider these stress loadings. For instance, if I increase the temperature from 25 to 50 and hold it, and drop it down to negative 10 degrees Celsius, and increase again, and then I collect the power consumption like this. Okay, and also I have another two of the stress loadings, temperature loadings, and this on the other, well, these three charts shows power consumption, collected using a power meter. Now, people think, okay, wow, when I do reliability tests, especially accelerated life testing, even though accelerated test, but it's still going to take time. Sometimes it takes a week or a month to stop. So and who's going to pay the bill, right? Who's going to pay the electrical bill? So then, in other words, how we find actually and evaluate energy consumption in a reliability test. So, and then again, well, this actually the project is sponsored by National Science Foundation. So before I talk about the technical details, I want to give you a heads up. The question is, can we make reliability tests efficient and also green? So I will show you this heads up. So using our method for a benchmark testing plan, we can actually reduce 62.1% of energy consumption compared to a benchmark test. So which is significant reduction in energy consumption. Now think about it. Every year in the world, there could be thousands of millions of new products are developed and tested. If you can save even a small amount of energy in the world every year, you're going to save a lots of energy and lots of money at the time. So this just showed, but in this project, we actually did it. I'm going to show you what we did. And first of all, I want to say something about it. So the first step actually is based on the equivalent testing plan concept. And before we do that, we can consider, okay, first how to estimate or how to assess the total energy consumption of testing plan. Of course, we can just use these equations. It depends on your power consumption power and your equipment. You do just integrated the power from time zero until you stop the test. And we have a different type of stress loadings. You just sum all of these energy consumption together. That's going to be the total energy consumption of your experiment. And here I want to highlight one thing. The U is the input or the control signal to the equipment at time t, and P represents corresponding instantaneous power consumption depending on the control signal. And well, of course, first of all, the energy consumption of testing as equipment, it depends on how you apply stress loadings. And well, you see here, I use three different stress loading. Their energy consumptions are different, right? And also depends how long the test will be. If the test is shorter, of course, well, even though you apply the same stress loadings, the energy consumption will be smaller. And also depends on the energy consumption, also depends on how you control the equipment. For instance, you have an on-off control, you have a PID controller. So if your controller has very strong capability to control the temperature, for instance, to match exactly what in your mind, then if you control the temperature as hard as possible, that means you're going to consume actually more energy, Remember, you're doing very hard on controlling something, take too much effort. Of course, you're going to spend actually take more effort to do that. So again, well, the energy consumption depends on how you apply the stress and how long the test will be and how you control the test equipment. So this work actually involves both statistical analysis, optimization, and also control theory, use of control theory. Now, in this problem, we actually ask ourselves, can we conduct an accelerated path testing experiment that is statistical, precise, and also consume the least amount of energy? So this is the major problem we're asking ourselves, and also ask reliability test engineers. So they do this every time. One of my students is actually working for a big company. They are doing testing laptop computers. They do everything. They they have a tested protocols, but they have never worried about the energy consumption, actually the electrical bill, of course, what they heard about, but they do not have did not have the methodology to deal with such problem. So this problem we come up with a new double loop ALT experimental design methodology. We have an outer loop where we determine the optimal experimental design, just like what we did before, or we care about statistical performance, like a precision of a reliable estimate. And in an inner loop, we're trying to control the design. We're actually just consider controller design and do energy assessment. And we need to determine if do a feasible analysis and the design of controller. And also we do energy assessment using a simulated control process. And to do this, we consider two methods. One is one step at a time. Another one is simultaneous method, optimization method. First, method number one, two-step ALT experimental design method. We optimize the actual optimization of the statistical efficiency, followed by energy minimization through optimal design of controller and of test equipment. And the second method is a fully integrated double loop ALT experimental design method. We simultaneously optimize statistical efficiency and also minimize energy consumption, and specifically consider solving a multi-objective optimization problem. I'm going to quickly go through these two methods and show you some examples. Method number one, two-step method for designing statistical and energy efficient ALT plans. We have already learned from the equivalent testing plan. We first solve for traditional design problem. We find a statistically precise benchmark ALT plan, and then we evaluate energy consumption, and also consider the constraint that we want to come up with alternative design which achieve the same statistical precision as the benchmark ALT plan. At the same time, we want to minimize the energy consumption of the alternative testing plan. And so basically we solve the problem two steps. We find the traditional design, solve traditional design problem, find a statistical precise benchmark ALT plan, and then next step, we find the equivalent testing plan and try to minimize the energy consumption associated with the alternative testing plan. And the decision variables are the following: the settings of the alternative testing plan and also the setting of the controller. So as I said, this project involves both optimization, statistical analysis, and the controller design. Now, as a demonstration, I consider what if the controller of the testing equipment is simply the PID controller, where we can have a capability to adjust the KP, KI, KD parameters. So this is adjustable PID controller. And we do this as a conventional PID controller. We try to minimize the tracking error. And as I said, if you have already developed a testing profile, actually in your term testing plan, you need to make sure your testing equipment can follow the stress profile as accurate as possible, but do not have to be perfect. As I said, if you try to follow the stress profile exactly 100%, it's going to cost you more energy. because we're going to take more effort to do the controlling parts. And also, we try to minimize the energy consumption during the test. Now, this is the simulation model we come up with. It's actually in math app in Simulate, we actually can find it's the energy consumption. Also can show how the equipment follow the signal, so that we can actually follow the stress profile. And this one is another one. So what if your controller cannot be adjusted? So basically your KP, KI, KD parameter of your PID controller cannot be changed. So how we do this? We actually can consider so-called input weighting PID controller. We just add this part outside of the PID controller, so we can still change the parameters of the performance of the PID controller, original PID controller. And so then design problem becomes how to determine these parameters, FP, FI, and FD, instead of changing the KP, KI, and KD in our original PID controller. Now, this is the simulation model we developed. So thanks to my former PhD student, to actually, again, just to evaluate energy consumption, how the equipment going to follow your test profile. Give you one example. If you're consider reliability model like this, and you have planning values for the parameters, our resources and the constraints are the following. We want to test 100 test units, and test must be completed within 200 hours, and your capability, the equipment, the temperature should go actually within 75 degrees Celsius and 150 degrees Celsius, so that we can accelerate the test. And also the ramp rate of the equipment cannot go beyond 2 degrees Celsius per minute, because the capability to test equipment is limited. So under those constrained resources, we consider one case. Well, this case actually is have an adjustable PID controller, and this is a transfer function of the test equipment, and we can actually power consumption can be evaluated in using this formula. And we do this first step, we find the statistically precise ALT model, and then the second step, we find alternative testing plan that achieve the same statistical performance of the testing plan achieved in the first step. Then we minimize energy consumption. Well, the second this equation constraint actually equality constraint, so which is tells us we need to find a alternative testing plan that achieve the same asymptotic variance and reliability estimate. And also we have this equation here that shows signal, how we generate signal, and how we evaluate this equipment response to input signal, and other constraints. Of course, we need to use Laplace transform in here to do this modeling. And turns out, so this is the benchmark statistical plan, and this is our alternative testing plan we come up with in the second step. And then this is the setting for our PID controller for this testing plan. And see here, initially this is a ramp stress test in our benchmark plan. And turns out we only need to use this, ramp test of stress, and we put all the test units and test all the units under these alternative stress loading, and we can evaluate the energy consumption. So we'll compare the energy consumption for the benchmark method testing plan. We will consume this amount of energy. So it's 30 million, some units of energy. But alternative is only 5 million. So actually it's a big saving, almost actually more than 50%. And this shows the control signal. So another example, so what if the PID controller is not adjustable? We just determine FP, FI, and FD. And we do the similar thing. Again, we just come up with the equivalent testing plan in the second step. We do this and evaluate everything using our simulation model and optimization model. We find it. Of course, in this case, we consider different cases. What if the PID controller is overdamped or underdamped? We have a capability to do that because we use a import weighting method to deal with the uncapable PID controller. We can deal with it. And And turns out this is the results. So the benchmark plan, even though we have underdamped or overdamped, um, equipment, we can change our PI, PD, well, actually PI, KP, KI, KD, but the total energy consumption is still a huge number. Well, but when we use our alternative testing plan, this is stress loadings and testing time is determined. We can find our best setting for FP, FI, and FP, and also shows energy consumption. It's even smaller compared, it's much smaller than the benchmark plan. So, in other words, we can use even for different cases, the PID controller is adjustable or unadjustable. We can always deal with the controller design to try to minimize the energy consumption. The second method, I will quickly go through this simultaneous optimization approach to designing a statistical and energy efficient ALT plan. So instead of considering optimization in two steps, we consider solving the optimization problem in one step. Well, of course, when we do this, we need to simulate the energy consumption, also the simulate the stress, how the equipment responds to the control signal. So, but in this case, we consider even more. Want to consider not just energy consumption. We also want to minimize asymptotic variance of reliability estimate so that we can get more precise reliability estimate. And also the last objective, F3X, we also want to make sure that the root mean square, basically we want to make sure the actual equipment stress profile follows the actually intended stress loadings as accurate as possible. And this is something. So I don't want to actually make the actual stress profile too far away from the intended stress profile. Otherwise, it's going to be affect estimation as accuracy, not precision accuracy, is going to be affected significantly. So our desired statistical, precise, and energy efficient ALT plan will be this. Actually, these are decision variables we come up with. We need to determine the stress levels, how we apply the stress, and how we allocate test units, when should we stop the test, and also the design of the controller. And also we consider different strategies, and we use, since we need to solve multi-objective optimization problem, we use multi-objective evolution algorithms. And to solve this problem, let me quickly go through this very quickly. So we have the coding, the tool we developed, and we can find solve the multi-object optimization problem. And this is a one numerical example, and we consider Y-body distribution for the reliability model. And we have also we consider the log linear life stretch relationship in this model. And then our goal is try to estimate the natural logarithms of 10% quantile, reliability quantile at the normal condition. And we have some resources constraints needs to be considered. 50 units available, and test must be completed less than 380 hours, and the temperature must go from a -25 to up to 150 degrees Celsius. Then this is the formulation, full integrated ALT planning process, and we have three objective functions. We solve it simultaneously. We can find this actually shows a Pareto optimal solution in a 3D space, but only consider the root mean square for the temperature profile and also the asymptotic variance of the reliability estimate. And we can plot this 3D plot for other combination of objective functions. And this actually shows when we have adjustable PID controller, and we can determine, okay, which one, consider different criteria. This one, solution number 6, bottom here, and provide a minimal energy consumption. Number 1, star, it provide optimal estimation precision. Number 4, provide minimal root mean square, basically provide the best, actually follow the stress profile the best. But overall, consider we actually need to make select the estimation precision our first priority, and with also considering other criteria, we pick the one actually number one star. That's our overall object overall design. And well, compared to the one step at a time method, and our this simultaneous method actually is better. Of course, well, we can. If you look at this table, it shows the total energy consumption. Simultaneous optimization method achieves smaller energy consumption and also achieves smaller asymptotic variance for reliability estimate, actually failure time quantile. And also even though the root mean square for the for the profile, you know, is stress profile is a little bit higher, which is worse than the sequential optimization method. But overall, we have to consider total energy consumption and the symptotic variance. The simultaneous optimization method is better. And also for unadjustable PID controller, we do the same thing. And you can actually imagine we should be able to get a similar answer. And of course, while the simultaneous optimization method achieves better total energy consumption and better reliability estimate precision. And of course, the root mean square for the stress profile is a little bit higher, but it's not a big difference. I think we can live with that. So this method actually further reduces the energy consumption by 8.1%. I think is probably not big enough, but actually, if you consider millions of product development testing process, this is a big saving, and also improve this estimation precision by almost 10%. And I have a couple of concluding remarks. I went through so many slides today. I do my best to introduce some of the concepts as quickly as possible. First, reliability testing and statistical analysis and optimization should be fully and carefully used in developing reliable products. And the last one is when you eat salad, use a fork instead of forklift. This is the final comment I have for today's tutorial. And thank you very much.
Thank you very much, Haitao, for the tutorial. I think you touched upon so many topics, and that gave us just a very broad overview of the fields of reliability. So, are there any questions from the audience? You can either type them on the chat or you can unmute yourself and ask. So while we wait for questions, Haitao, are there any software, user-friendly software available for reliability analysis that you can recommend?
Yeah, there are, but okay, I don't want to do commercial, but a company they used to have called the name RelySoft. They actually the boss actually start developing the software when he was a master's student at the University of Arizona. So he developed, and then he developed software, and some of friends have been working in that company. And several years ago, he sold the company, I think, to HBK company. That now the HBK company owns RelySoft software. So RelySoft software can do viable analysis, can do fault tree analysis about different packages, and also can do one package called ALTA, can do accelerated life testing analysis. And also they have a DOE package. What else? The FMEA to also can do system reliability estimation. Well, actually, if you consider different structures, a system, well, the software can find a system reliability for us. So it has to provide a closed form expression for system reliability. Sometimes you think it's even very hard to come up with the minimal cuts. The software can help us determine the minimal cuts and also determine the importance of each minimal cut. Yeah. And also some software like Jump, of course, Jump, provide us reliable analysis, of course. While the Dr. Meeker actually is one of the biggest player for jump,
Yeah.
definitely. So I think Bill Fisher, he knows very well. Absolutely. So actually, I had the so Dr. Meeker used yearly and Dr. Alcid and Win Nelson. They used to provide offer tutorials at Rams and other places. Um, they had almost every last in past several years, almost every year I met them at the Rams conference. I took some pictures with them. But now Dr. Meeker retired, and also I think Dr. Win Nelson, he stopped offering tutorial at conferences. They are big contributors to the community, so they actually provide. I personally learned a lot from them. Remember one year when I gave a tutorial on degradation analysis, he was there. He criticized my my terminology. He said, "Okay, talk about the inverse power." I talked about the inverse power law. He said, "No, no, 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 it's not the power law." He talked about it. It should talk about the name of the inverse power rule, something like that.
Mm.
Law is something stronger, so that's what
Yeah.
I learned from him. So there are a lot of interesting conversations between these people themselves, and also I was happy to join their discussion sometimes.
So, any other questions from the audience?
I have a quick question. I'm wondering in terms of time, how complex are these optimization problems you're solving for both the two different strategies? Do you have a
Yeah,
rough
yeah.
estimate on?
I would be honest with you. So most of the time spent on evaluating the energy consumption using the simulated model. That takes time. Well, because it's not well, you have to simulate, the how the equipment responds. Then you have to when you change the parameter settings, either it's the adjustable PID controller, you have to change those parameters. You have to change it, then evaluate, change it, evaluate. It takes time. So I think at the time that student was um, graduated from actually that the work was done when I was at the University of Arizona. So my PhD student, graduated many years ago. Um, so I still remember at the time she told me, Dr. Liao took time to do this optimization and take probably a couple of hours to do the evaluation, uh, which is acceptable for such complex optimization problem. Of course, that's why we want to do use the consider two-step approach. Define the equipment testing plan and just to simply optimize the controller will be much easier instead of consider optimizing the setting of the equipment, setting of the testing, and also the setting of the controller. It will take more time.
Yes.
But
And
turns
then
out the
in the
sequential method, the two-step method, actually doesn't take too much time. It's probably an hour or sometimes less than an hour.
so for the two-stage plan, is it generally pretty easy to generate? Like, given that you've solved, like, you find like this statistically efficient plan, is it easy to find and generate equivalent plans, or is there
That's right.
typically
That's
quite a
right.
few of them?
That's not
Okay.
that's not too difficult. So I showed the equivalent testing plan theory. So
Yes.
it depends if you, especially if you consider a general equivalent test plans, is very easy. Is to make sure the
Oh,
two objective functions are exactly the same. But if you want to find the type three equivalent testing plan, you want to make the two variance convergence matrix exact the same. You
mm,
have to solve these a set of nonlinear equations. Depends on how big the variance convergence matrix is. But the one parameter embedding methods can solve it. At last time, I just click, 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 done. Doesn't take
I
much
see.
time, of course, but it solved the nonlinear equations. Works very well.
I see. Thank you.
Thank you so much.
Any other question? So Haitao, in a way, I mean, your research can also be thought about, well, thought as like how can we preserve the products, like uh, so that they last long. So in that regard, do you have any recommendations? With batteries, for example, they don't like cold because that will degrade them faster, let's say. So have you seen something, like any advice on any common products that we use, uh,
Well,
ways to preserve
oh,
them, just like for the regular
good
human
question.
beings, let's say?
If you do not, uh, if you can keep the operating condition as stable as possible, be better. So, if, for instance, if the operating condition is not well controlled, basically you're subjecting your what product to time varying conditions. So sometimes, for instance, if you subject a product to temperature cycling, it's going to cause more pheromones. For instance, fatigue is a big issue for if the thermal cycling is applied to a mechanical product or material, for instance, like a composites material. It's going to cause a lot of trouble, lots of trouble. So, but if you consider a fix, make the operating condition as constant as possible or as stable as possible, then the reliability of the product can be good, maintained very well, better, not very well, actually, as expected.
Hmm.
And actually, nowadays, people, even though we are trained in the reliability engineer field, so we are trying to extend our efforts to the food industry. Yeah, the food, because because similar things like shelf life,
Yeah.
but the food. And it's an interesting problem. So I don't know if you like blueberry.
Hmm.
You like
Yeah.
think about it. People actually, after they harvest a blueberry, they put it in a basket and just put it in a storage. They don't wash it.
Hmm.
If you wash blueberry, it's they're gonna degrade. Blueberry gonna degrade much faster.
I see.
So it's
Interesting.
something, lots of real world problems needs to be considered when we talk about the life, shelf life of the foods. Veggies or fruits or something.
All right. All right, everyone. So I think we can conclude now. Thank you very much for your attendance. Thank you very much, Haitao, for the tutorial. I'll stop the recording.
Thank you.